Hey, calculus time again. Welcome back, all. Adrian, Jesse, good to see you guys. Eve, good to see you. Laisha, good to see you. Gabriella.
How was your break?
Good. How about yours?
It was good.
Seemed like a long time. Did you guys forget everything you knew about Calc 1? Maybe. Excuse me. Welcome to Calc 2, my friends. And I'm excited to show you this side of the universe. Got some new folks in here too. Vale is here. Thomas, good to see you. Let's see. Let's just check a couple of quick things out while we are getting our minds around this whole business. So the people from last term in Calc 1 are no strangers to this, but just want to make sure you guys all get on board. I haven't checked this recently, but looks like tons of you are on board with this. I see 14 messages, which is what I'm getting if you've logged into this. But if I go into, for instance, the grade book in here, of course, we haven't done anything yet, but I should see your name right there. So on my syllabus, and also a sheet that I sent earlier gives you access to this. It's a free online homework program, which is really cool because all you had to do is buy the book instead of the whole Pearson side of this course. And that's working pretty well. So get yourself loaded into that. We're going to launch right into it today. We're going to be spending 2 days on 5.1 that you may have saw in the syllabus. But those assignments are all sitting in here. So here is 5.1's assignment. Every one of these sections, you probably will never read this stuff, but I just have a list of things we're going to study. So just as a for instance, right now you should say Riemann sums. Have no idea what that is. Left, right, and midpoint approximations. Have no idea what that is. Sigma, that's Greek letter sigma notation. Have no idea what that is. And so anyway, that's what we're going to be talking about in that section. There's a bunch of videos in here that I stole offline from different people. They're just kind of backup that you might want to look at. It's in a sense, these are not designed directly toward, they're designed toward the topic. So it's kind of like a little mini lecture about one problem, if you will, that's kind of related to what we're talking about. So if you ever have time or want to get more of a, deeper understanding, like in a sense, area under the curve with rectangles, that's what I'm going to show you in just a minute. So, there's another take on it, if you will. And then here's our homework assignment. So all of our assignments, just as a reminder, this is on your syllabus too, but they're all basically due the following Sunday. So you sort of have all week to work on them. And as I always say, if you want to kind of do this the smart way, the thing to do is to kind of do it immediately. That way you have time either after class or before class on the following days, to bring up questions and say, hey, I really struggle with something. Also, and I said this last term too, but this program is free, which is wonderful, but it's also the first time that we've taught through it. So there may be issues with it. We had 3 or 4 questions last term we had to fix because, they were coded wrong, which again, I apologize for. It's hard enough to learn this stuff if you're getting it wrong when you think you're right. But I want to get to the bottom of that. So don't automatically assume. And as I said, it was 3 or 4 times. It wasn't 20 times. So it's mostly on the ball. These are problems that other instructors have written in other colleges. And so they're they're stolen from other places. And so also, you just may have things, I don't necessarily teach to the assignment. I look the assignment over before I teach, but you may have questions about this that, we need to talk about in class. And so don't be hesitant about asking those kinds of questions. So this is the online homework platform. And then inside here, every day I'll be posting class notes. I'm going to post what I write for you. Again, those of you in last term already know this, but I'll be posting whatever I write in here. And so I would prefer you kind of split your time between paying attention and writing, because whatever I write, you don't need to write. I'd rather you be present and asking questions, because as much as possible, I want this to be a conversation. So so it's two-sided, and to that end, I want you to call me Doug, so that we're on a first name basis, and I want you to interrupt and ask immediately. Don't wait till the moment's passed. I actually, one of my favorite things is when you interrupt and say, didn't you make a mistake right there? And actually I didn't, because that shows that you're willing to talk, you're willing to speak and think, and it gives people time to think. Teachers tend to talk too fast. So so are we okay? Let's see. The other thing the syllabus talks about is the fact that there's take-home quizzes. So this first take-home quiz is not due for a long time. It's over a number of the sections. So I'm going to be grading these before the test that we take over chapter 5. And this gives you a chance to, write things out. And also gives me a chance to kind of give problems about what I think are the most important things. Which is kind of extra practice for you, but it also is kind of along the lines of what you're actually going to see on the test. So sometimes when you're just clicking buttons on an online homework assignment, you're not as prepared to do the written version of a test. And so this gives you a chance to kind of practice that a little bit too. And so, and again, with respect to these problems, you're going to open these. It's just a link in here to a paper, and the best thing to do is to print the paper off and write on it. And then I talk in here about how to scan it with your phone or with a scanner, like a printer scanner at your house, and send it back to me as a PDF file, because I'm going to write on it and grade it and get it back to you. And that's the most important part, because if you're doing something wrong, I want you to know that before the test comes. So you're getting it to me and in time for me to grade it and get it back to you. But you should get 100% on this, because you can ask me questions about it. You're more than welcome after class to say, hey, this is what I got for question 7. Is that right? And if I say, yes, it is, then you can say, okay, good, and we're done. If it's not, then I can look at it and we can talk about it a little bit, and I can give you some hints. You're more than welcome to compare this with other people in class. Obviously, you have to do your own work, but the goal is to get these questions right, not with whoever's help, my help, your own thought, or somebody you meet with outside of class, so that you're learning. It isn't just another assignment. This is a pain in the butt for me to grade. The online homework grades itself. And so make sure you use this to your benefit, but also start early. It's not due until, I forgot the due date, went past me there, but it's not due till the 25th. And so it's like 2 weeks from now. So don't save it for the last night, but you have plenty of time to be working on it if you don't save it till the last night. Let's see what's in here. Syllabus. Okay. Anyway, I don't want to ramble about stuff that's not necessary. I want to get on to what we're doing. So let me give you an introduction to what Calc 2 is all about. So I'm going to share my screen and get this rolling. Okay, I think technology is working and you are seeing a blank screen. And so this is the beginning of what I was talking about. I'm going to be writing on this, and everything I'm going to write, I'm going to post right after class. So Calc 1, for those of you that joined us in this class, I'm assuming you took Calc 1 earlier. Perhaps you took it last term and it's still fresh in your mind, but you may have taken it a term or two ago and may not be super fresh in your mind. But just to reiterate what we did in Calc 1, which was kind of the derivative calculus, which is really, as I kind of jokingly said to my classes last term, is just slope. So we don't tell people that all we're really doing is studying slope in calculus, because we like people to think that we're smart, and this is really hard, but it's not. It's the slope, but it was the slope of a curve. And so what was novel about calculus is we, for a person in Math 60 to say, what's the slope of that? You'd think, well, how can you find the slope of it? It's not a line. It has like a low slope down here and a high slope up here. And so you can't really talk about the slope. And so in calculus 1, derivative calculus, we said, yeah, you can find the slope. You just have to pick the point you're at. And so, okay, we picked a point. We're at that point right there. And so how are we going to find the slope? And embarrassingly, we said, well, all we're really going to do then is just pick some other point that's really close to it. And then we're going to find the slope using those 2 points. And what made calculus novel was the fact that we actually let those 2 points get infinitely close to each other. And therefore, they actually ended up touching. And the miracle of it was that didn't explode. That it actually worked. And so we touched infinity. We let those things get infinitely close. We didn't just automatically start out with them being the same point, because then slope would have been meaningless. If this is the point 3, 2, and this other point was also the point 3, 2, when you go y minus y over x minus x, you get 0 over 0, and it doesn't work. But if you get a little creative as to how you write that down, and you save that, you save letting the second point also be 3, 2, you save that for later, then you actually do get not just the slope, but the exact slope at that point. And so we touched infinity. We let those things get infinitely close. And to that end, Calc 2, which is what we're looking at now, which is called integral calculus. We're going to touch infinity again, and let me show you kind of how that works right now. Let's do the whole thing. We're going to do the whole concept of all of Calc 2, right now in this class, in this discussion. So let's consider, let's see, x squared. Let's consider that equation right there. Parabola moved up 1. So if I make a graph of this, I'm tempted to go into Desmos and make a good graph, but I think we'll just tough it out here. So there's the right side of our parabola, and I'm purposely only going to look at this parabola, let's say from, I don't know, let's go 0 to 2. So we're only going to look at the parabola from 0 to 2. And I think I'll just consider that whole thing as being written out in that way. So there's 0, there's 2, and we're looking at that graph. And so you're familiar with that. You're familiar with the graph algebra and so forth. But what is it we want to do in calculus? Well, we now know from Calc 1 that we could find the slope of that curve any place we want. And really, integral calculus has to do with finding the area under a curve, or a little more profoundly than that, basically just strange areas. You have geometry formulas that you're vaguely familiar with that tell you how to find like the area of a trapezoid. And so even though that's not a nice rectangle or a triangle, you have a formula for that. And you can figure it out because the sides are straight, but you've never touched anything curved before. Well, with the exception of the circle. And that was and I mentioned this a little bit last term introducing Calc 1, but that was there's quite a history there too of people trying to figure out, as the ancients called it, how to square a circle. and basically what they meant by that was how to make it rectangular. Because when you say something is 2 square inches for its area, that literally means 2 inches that are 2 square inches, that it's 1 inch by 1 inch. 2 of those would fill that space up. And so how do you fill a circle with squares? Curves are quite a problem. And so in Calc 2, we're going to say, can we find the area of something curved? And so for right now, out of simplicity, we're going to say the area under that curve, and even more limited by saying it's under the curve from 0 to 2. So we're gonna find that area right there, which again should be impossible. How are you going to fill that up with something that's square? How are you going to say that's 2 square centimeters? How are you going to fill it with squares when it's got a curve in it? And the idea here is embarrassingly simple. So let's do this. Let's say we decide to fill it with n equals 4 rectangles. The only thing you can actually really find the area of is a rectangle, since the area is base times height. And so let's fill that with 4 rectangles. And so if I did that, would you agree that if I take, since this went from 2 to 0, if I say the width, I'm trying to figure out the width of my rectangles. So I go 2 minus 0. In other words, my distance is 2, and I want 4 rectangles. So I'm sort of getting a width of a half. And again, you probably just did that in your head. You probably don't need to write that out, but we will for more complicated problems later on. And so if I divide this up and I say, okay, now notice I haven't made any rectangles yet, but every one of those is 1/2 wide. Now it seems sort of pointless and stupid, if you will, and I'm going to do this. How am I going to define the rectangles? Well, their widths are all 1/2 across the bottom here, but their heights are all different, right? So I'm going to have to add these things up. Every time I move to the right, the height of my rectangle gets a little bigger. Well, you should say, well, those aren't rectangles. They're more like trapezoids, or something like that. And even, they're not even really trapezoids, because the red shape is curved, but they're closer to trapezoids than they are rectangles. But one option is I could do this based on what we're ultimately going to talk about is a right side. In other words, I'm going to define the height of this first rectangle, not by its left side, but by its right side. Does it make sense? That makes it too tall. It's sort of too big. And so I'm going to say, what's that area? And then this one over here, the second one, I'm also going to define by its right side. And so again, that makes it too tall, and so on and so forth. And so if I add the area of those 4 rectangles, does it make those 4 green rectangles, does it make sense? That gives me an approximation for the area. Now, would you agree it's sort of an embarrassingly simplistic approximation? Like it's going to be off by a lot, and you can even tell it's going to be too big. But again, just to make sure you understand the simplicity of the idea, last term in Calc 1, it was slope, y minus y over x minus x, the entire term. And what I'm showing you right here is what Calc 2 is, the entire term. It's the area under a curve by just using a bunch of rectangles. Now, because calculus touches infinity, perhaps you can tell where this conversation is going to go from here, but let's just go slow. I'm giving you a couple of days to spend time trying to make sense of all this, and I want you to get it deeply. So I've got to get this sum. So let's see, what have I got? Well, how do I get my heights? You tell me this. How do I get the heights? I know the widths of my rectangles, but how do I get my heights?
You would just put each one of those into that function.
Exactly. The heights you get by plugging the x coordinate into the function. So for this first one here, I'd say the width is 1/2, and the height would be the function evaluated at, well, remember I called it to the right-hand side. So let's go over here. It's evaluated by that point there. If I would have started over here, a left-hand side, I would be sticking 0 in to see how tall this is, but I'm sticking in 1/2. So would you agree that's the width and the height of that first rectangle? And then I'm going to do it again. 1/2 times the height of the second rectangle, which is over at x is 1. And I'm going to do it again. times the height of the next rectangle, which would be 1.5 or 3/2. I probably should say 3/2. And then lastly, 1/2 times f of 2. And of course, this is, slow. Got to bust out my calculator. I guess I really don't. I could probably do that in my head. So let's just go slow here. Well, first of all, just to save a little time, do you agree they all have a 1/2 in them? So I could actually just take that 1/2 out of all of them. Let's see, an f of 1/2. 1/2 squared is a fourth. 1 plus a fourth is 1 1/4. So there's kind of that first height. And then when I put 1 into there for this next term, for the second rectangle, 1 squared is 1 plus 1 is 2. And 3/2 squared would be 9/4 plus 4/4, I think, is 13/4, which is 3 1/4. It's dangerous doing that in my head. And then this last rectangle, when I put 2 in here, 2 squared is 4 plus 1 is 5. So let's see, I can do that in my head too. 7, 8, 9, 10, 11 and a half. So I have 1/2 times 11 and a half. So I get 5.75. Now again, you've never done this before. Nobody's ever asked you to even find the area of something curved like this. And so wouldn't you agree this is kind of the simplest approach you could take? Just, stick some rectangles in there. And would you further agree, as I mentioned a second ago, that this is clearly too large, right? Based on the picture. So let's brainstorm a bit. What things could I do to improve this?
More rectangles?
Yeah, 1, more rectangles. What else?
Subtract all the triangles.
Yeah, go back and try to kind of look at those little triangles up here and try to figure out kind of what size those are. And again, they're not really triangles, right? Because it's curved, but they're close to triangles. And so if all I'm trying to do is approximate this, I could try to get at what size are those triangles and subtract them off.
Since we know how to do derivatives and slopes of curves, couldn't we eventually use that to find exactly?
Yeah, maybe something with the fact that I know what slope is and I can figure out kind of what angle those triangles are, if you will. Is there some way I could ultimately get it exactly right? So maybe calculus would allow us to get at, and that's kind of related to this second point, I think, do something with those triangles up there.
Here's an idea. I think that the thinner that those rectangles get, so like the more rectangles you put in, then eventually you don't really have to worry too much about the triangles if there were like infinitely many rectangles, like we did with the slope.
So what Felix is doing, in a sense, is adding a little bit more credence to this idea. In other words, if you have not just more rectangles, but a lot more rectangles, does it make sense that the wasted space in those triangles up there starts to go away? And if you really get a lot of triangles, meaning, well, infinitely many rectangles, if you have infinitely many rectangles, then that space really does go away. So that's not a bad idea to have more rectangles.
Can you measure the height from the left-hand side?
Yeah, you said this was the right one.
Yeah, what if we measured it from the left-hand side?
What if we measured from the middle?
Or what if you measured from the middle? Everybody, do you see the logic in this? In other words, I think I'll erase this just because it'll probably screw the picture up a little bit. But what if I went to the center of that rectangle and called that the height? Does it make sense? Now you'd have about as much too big as you missed. Does it make sense? That would do a really good job of balancing it. And again, these are all approximations. But there's just all kinds of creative things you could do. So let's see. I'll just abbreviate height to the middle. Of the rectangle. Related to that, I forgot who said this now. Related to that was kind of the concept of not doing a right-hand side, but doing a left-hand side. Does it make sense? Let me just draw a quick picture of what would happen if we did the left-hand side.
Wouldn't it be still kind of hard because you're missing now under the curve? Instead of overshooting, now you're undershooting?
Exactly. And that's what I want to make sure you see. So if I measured to the left side, does it make sense the answer is going to be too small? So you're still going to miss it if you go to the left side. Does that make sense? But what could you do if you had the left and the right side?
That would create a square, right?
That kind of gets at this triangle business. You know, we're talking about kind of doing something with the triangles. Does it make sense if you had sort of the too small answer and the too large answer, that if you average those two, that'd be a really good approximation? Now it'd be perfect if those were actually triangles. But since this is curved, averaging those two is still not going to be perfect, but at least as an estimate, it'd be a whole lot better than the one we just got.
Wouldn't that be similar to doing the one where you just set it in the middle?
Yeah, that's exactly right. And setting it in the middle would actually do that without having to do both. Very good. The only other thing I can think that I alluded to a little bit earlier, maybe I'll just write here, average the left and the right. And I'll point out, as Eve just pointed out, that these two ideas are actually pretty similar. They're actually the same. And even related to that, kind of a fifth concept is, does the shape that we're using here have to be a rectangle? Couldn't we approximate it with a trapezoid? Don't we have a formula, an algebra formula? You may not remember it off the top of your head, but don't we have an algebra formula for if it was a trapezoid? And again, let me draw a quick picture of that, because really what I want you to do is just have time to soak on this idea. So a trapezoid would be where you came back and said, there's a trapezoid. Notice that trapezoid has a different angle. This trapezoid has a different angle. And that trapezoid has a different angle. Does it make sense? That's going to be awesome too, as an approximation. Now it's going to take a little more trouble, right? Trapezoid formulas are a little more trouble. You got more heights to figure out. But these are all the concept of what Calc 2 is really about, is just finding curved areas. And so oddly, and again, almost embarrassingly, what we're really doing in Calc 2 is saying, well, let's just fill it up with shapes that are, you know, ordinary, boring shapes. It just seems kind of low tech, doesn't it? As a technique. But what Felix alluded to earlier, the fact that if we're somehow able to not just do this for 4 rectangles or 40 or 4,000, but actually infinitely many rectangles, then the error starts to go away, and then we can just stick with boring old rectangles. We don't have to average left-hand sums and right-hand sums. We don't have to make trapezoids out of them. We don't have to figure out where the middle of each rectangle is. Can you appreciate that's a kind of a hassle? Like a second ago, we plugged in 1/2 and 1 and 1 1/2 and 2. But to go to the middle, we'd have to think a little harder to figure out where the middle was. So as a solution, if we just let there be billions of rectangles, then we could just let them be rectangles. And if there are billions of rectangles, we actually don't even care if it's on the left-hand side or the right-hand side, if it's a little too big or a little too small, because if there's not billions of rectangles, but infinitely many rectangles, then we don't even care which one, because now it's perfect. But of course you should say, well, this was fairly time consuming just with 4 rectangles. So how am I going to add, I mean, even 20 rectangles, like the 20 rectangles would be a good estimate, but it's going to take a long time to add these, and so unless there's some trick or some magic, and didn't you see magic in Calc 1 where we started out going f of x plus h minus f of x over h, and that was quite a tedious process, and then we realized, hey, there's all these amazing shortcuts as to how to find the derivative, the equation, how to find a new equation from the original equation that would just tell us the slope, and we didn't have to actually go through the process. And the brilliance of Calc 2 is we're going to get to add infinitely many rectangles together, and we're not going to have to add them together, thanks to calculus, thanks to the fact that we can touch infinity. That's the big picture of Calc 2. Basically finding a curved area. Go ahead.
This might not actually end up going anywhere as an idea, but it kind of looks like all the different functions in the sum are just kind of like a line, and that would be, maybe you would get like a line that's a lot easier to find area under. But
in other words, you're looking at this thinking, is there some kind of a pattern to what? I think I'm understanding your question. Is there a pattern to these numbers we're kind of adding together so that we can, add them without having to work so hard? But I do want to take a second and make sure. I want to see if this.
In the spot where you're putting the rise, essentially, couldn't you at that point use the function for the derivative in that spot and do the derivative of that specific point?
I think I understand what you're saying. In other words, you're going back here and saying, boy, my drawing looks really terrible when you get close to it. You're saying if I, go back to this spot right here and the rectangle's not so wide, could I use the slope, the fact that I know what the slope is, to sort of figure out where it takes me to the next point?
Yeah.
Yeah, I mean, that's brilliant. And then oddly, that's kind of why this is still calculus, I guess. Why this topic, which seems so different in the previous section, we were saying what's the slope of a curve, and now we're saying what's the area under curve, and they sort of seemingly have nothing to do with each other. And yet, Jesse's trying to say, is there some way we can kind of get them to work together? And the answer is yeah.
Jumping off their related topic, this kind of does make me think of calculus, because I think the first day of Calc 1, you told us you drew a circle and you talked about octagons and adding infinitely many sides to get close enough. Was that Calc 1?
Yeah.
I think that was.
That's exactly right. And because it was a circle, we let there be infinitely many triangles. And remember, they really couldn't be triangles because the top of that triangle was a curve. I won't belabor this point too much, but the top of it was actually the curve of the circle. Therefore, it wasn't straight. But if we let them be infinitely many and infinitely thin, now the fact that it's curved is not that big of a deal. And the same thing is true here. There is a curve we're finding the area underneath, but if we have really narrow rectangles, then for all intents and purposes, that top edge is straight. And that's kind of the same thing here. That's exactly right. And so that's why I'm saying really ultimately calculus is touching infinity more than two separate topics. Like let's find the slope of a curve and let's find the area under a curve. It's touching infinity. And that's what I'm getting at when I say this should bother you a little bit. If we say, great, let's just have infinitely many rectangles. And if you're telling us, Doug, that we're not going to have to actually add them, then great. But if you have infinitely many rectangles, what is this little sum going to look like right here? What's that going to look like if I write that out? Well, What happens to these numbers? Well, there's just going to be more of them. There's going to be 1 1/4, 1 5/16, 1 6/16, 1.78, 1.99, 2, 2.01. There's going to be tons more numbers here to add.
But what about the width? Because before we were able to find the width, now we can't find the width because it's infinity. And how do you divide infinity?
How wide are the rectangles? If you have infinitely many of them, then how wide are they? I do want an answer to that if you want to.
Well, they don't have a width, or at least they're infinitely close to not having a width.
Yeah, basically then this is on its way to 0 because they're going to be really narrow, right? So for a while, they're like 0.1. Well, that's pretty small, but it's not 0. They're 0.1, but then they're 0.01. And this is where I was getting at before, this little formula that I wrote up here to get the width. Don't we have to take our 2 endpoints? Since we went from 2 to 0, I went, okay, 2 to 0 means we have a width of 2 to work with. And then we divide by how many rectangles we choose. And so if I come down here and I say, okay, what's our width? And I say it's still 2 minus 0, but what if we have 1,000 rectangles now? Well, now your width is 2 thousandths. And you're going to have 1,000 numbers here to add up. And they're all big numbers. In other words, they're numbers from 1 to 5. They're 1s and 2s and 3s and 3.1s. They're big numbers. And so you're going to get a gigantic answer inside that parenthesis for all those heights added together, aren't you? But meanwhile, what's happening to this width out here is it's on its way to 0. So basically this is on its way to infinity. The actual heights of rectangles that you're adding up are on their way to infinity. You have a whole bunch of them, but your width is on its way to 0. So now you have this fight between infinity and 0. Who's going to win? Are you going to have, is the fact that the width of the rectangles is on its way to 0, does that mean that the area is going to be equal to 0? Or is infinity going to win and the area is going to be on its way to infinity? And you know, the brilliant thing is it lands in the middle somewhere. It lands at the correct answer. But really that's what this is doing. And so in calculus, it turns out the simplest thing to do, because there is a shortcut to this. If there was no shortcut, then calculus would not be a thing. Because if you wanted to approximate the answer, you'd have to get creative and try some of the great ideas that you all came up with. And by the way, if your goal is just to approximate, so I'm looking out at my grass right now and I've got this kind of kidney shaped lawn, kind of looks something like this. And I need to know the area so I can pay for the grass seed that I had put on it. Maybe I need to go get some fertilizer to put on it. So I need to know the area of that shape right there, at least an approximation of it. Do I care to do calculus on it and get it exactly right? No, I don't. I don't need to. And I didn't. Like, I know calculus really well. Did I just become a nerd and go out there and set up calculus and get it perfectly right? No, because it's a waste of time. Even though it's cool, I could do it, it's a waste of time. And so I just got an approximation for it because we're talking about fertilizer and grass. You know, it's not that important. It's not important to get it right. If you want an approximation for this area that we're describing right here, and in the real world, most of the time, that's all you need is an approximation. I'd say that trapezoid trick would work pretty darn good, wouldn't you? Or go into any of the ideas you guys said, go into the midpoints, go into the middle of the rectangle, and just taking kind of an average of it. Again, those are all kind of related ideas to each other. But I'm probably not going to go too far into this more rectangles business. Do you understand that? Because 20 rectangles is going to be really time consuming. And even the chances of me writing something down wrong, pushing a button wrong in my calculator, doing something stupid, I'm probably going to do that if I have 20 rectangles. And so, you know, fewer rectangles, like 4 here, except use trapezoids instead of rectangles, is probably going to work for most situations in life. And again, as I've try to say often in my classes, that's kind of the difference between a math student and an engineering student. Engineering students want to, you know, fertilize the lawn, build the bridge, whatever, and approximations are plenty close enough. And we have amazing technology like Excel that can add lots of rectangles. You know, it can add 20 rectangles and not screw it up. And we can say, hey, that's close enough. Let's move on. Let's build the bridge. True mathematicians say, yeah, but is there a way to get it perfect? You know, just because it's cool, just because it's possible. And, you know, the answer to that is yes. And to some extent, I hope you have a little of both in you. I hope part of you says, you know, let's live in the real world and just get this done. We don't need calculus. I hope another part of you says, really, there is a way to get this exactly right. And, you know, that's kind of cool. I mean, it's just kind of neat. I hope you still have a little of both of those in you. So just to let it soak in a bit, let's go back to our original problem. And so we're going to do this with rectangles. Like calculus deals with rectangles because that's the easiest shape you could possibly do. And because calculus lets us touch infinity, then that error is going to go away, which is Felix's intuition at the start. That wasted area, the area we always get wrong, is going to go away because we actually have infinite many rectangles. So let's just keep it at rectangles. That's what ends up happening in calculus because you can touch infinity without having to do it. And didn't we do that last term? We let 2 points get infinitely close, but we sort of didn't have to worry about that anymore. Remember at the end, we said, hey, what's the derivative of tangent? And it was secant squared. Maybe you remember that. And it was like, oh, cool, secant squared. That's a formula now that will tell me the slope on the tangent curve any place I want. And I didn't have to let 2 points get really close. I wasn't even thinking about that anymore. I just was able to use kind of the logic of calculus. And the same thing's going to happen here. So we actually are going to be able to touch infinity. And so we're just going to let it be rectangles and keep it kind of simple. But to just make sure you kind of, I don't know, soak on this idea a little bit more deeply, let's just do it one more time. But let's double the number of rectangles because I think I can handle 8. So let's let there be 8. And again, I'm really just giving you time here to soak this idea into your brain a little bit better. So I think my equation was +1. So I'm going to put that here. Let's see. So I need 8 rectangles. So their width can be found by going 2 minus 0. And again, that's because I'm saying I want to know the width. I want to know the area from 2 to 0. If I was saying I want to know the area from 5 to 2, I'd be going 5 minus 2 here. In other words, just trying to figure out how wide is the space you have to work with. And then divided by the number of rectangles. So that's a fourth. So each of my rectangles, my width is a fourth now. So let's go make that happen. So I can divide a half. And you might notice why I picked 8. I didn't pick 7. Why would it be painful to pick 7 rectangles?
Harder to divide it by hand.
Yeah, you're dividing it by 7 and you're getting this really weird. There's no reason you can't have 7 rectangles. But notice in my case, I divided it by 4. Now, if I divide by 2, again, I'm just cutting all of those in half. Do you see how easy it was to draw 8 rectangles, whereas it would have really sucked to have 7?
Same reason you slice a pizza into 8.
Exactly. And I want to do, let's see. Let's do a right-hand one again, just because I want to compare it to the answer we had before. Remember our last right-hand answer was 5.75. What do you expect to happen this time? It's okay to be wrong.
It will be a little bit smaller.
Yeah, there's going to be, Lee's right. There's going to be less waste. Didn't we have way too much area because of all those triangles above the curve? Well, because we have more rectangles, there's going to be smaller triangles up there, and we're going to have a better answer. Do you see the logic in that? So we're going to get something less than 5.75, but it's still going to be too big. And if we have 1,000 rectangles, it's still going to be too big. Do you understand that? It's always too big. If you pick rectangles, it's always too big, unless you have infinitely many rectangles. So, oops, I said right and I didn't draw right. Can you see what I mean by right and left side now? Right has to do with, well, how tall is your rectangle? Well, I'm going to define it by the right side of that space. You know, this space right here. How tall is the rectangle? I'm going to define it by the right side. Well, then it's going to be too tall. No, I'm going to define it by the left side. Well, then it's going to be too short. Neither of those really work. And we talked about how the middle is even better. So I'm choosing to define them by the right, which is sort of code for your answer is too large. Well, I should caution you that if the curve was going downhill like this, what happens if you define it by the right side now? Does it make sense that the answer is too small? So I can't just say the right side's always too big. You just have to decide which side of the rectangle you're going to go with. And again, if it wasn't for calculus, we would not do it this way. We'd use trapezoids or we'd use the middle. But because of calculus, we sort of don't care whether we choose the left or the right, because we're going to work our way to infinitely many rectangles. So in this case, too big. Our answer is going to be too big. We already know that. So let's see, what is my area going to be then? Well, let's save a little time and say our width is out front here. I don't want to write 1/4 every single time. And so let's see, what are these locations? Well, that's a 1/4. So I have f of a 1/4 for this location, and then f of a 1/2, and then f of 3/4, and f of 1, and f of 1 1/4, which I think I'll call 5/4, and f of 6/4, or 3/2, and f of 7/4, and finally f of 2. Didn't quite fit. So my width just got smaller, it got half the size, but as a result of that, I have twice as many rectangles. And so these are my heights. Can you already see that this feels like kind of a pain? So I'm going to cheat. What am I doing right now to cheat? Any of you have an idea? Like, this feels really time consuming. So how am I going to get all of these answers? Actually, I think I should show this to you. I should show you what I'm doing instead, just because you should be. I would say I wasn't that good with the graphing calculator, because your assignments are going to start out with things of this nature. Let's see, screen to share. So I'm going to cheat. What do I mean by cheat? Well, I'd like to plug those numbers in, but I don't actually want to do it. It's like too much trouble. I'm lazy. So I'm going to go in and type in this equation, because the graphing calculator will tell me these, but it's time consuming to even go in here and say, okay, I'm going to trace now. And my first one was f to the 1/4. So if I trace to 0.25, then there's your height, 1.0625. There's my first number. But what's a better way to do that? Do some of you know this? Because I need like 8 of these, right?
I think if you can go to table set, you can change like every little number and like the difference in between each slot.
Exactly. If you go to table set and you say, where do you want your table to start? Well, I could say, let's start at 0, although that'd be the left-hand side. I really wasn't starting at 0, right? I was starting at a 1/4. And how much do I want those to go up by? Enter. I want those to go up by, well, a 1/4. And notice it says auto, and I say, okay, great. Now if I say, now the table is set up. So if I just say second table and I go to table, see, there's all my answers. Now, again, I didn't really need 0, did I? So I could have said start at 0.25, but there's that first one that I got a second ago. So basically I need to add 1.0625. That's the height of the first rectangle. And then 1.25, that's the height of the second one. 1.5625, that's the height of the third, and so on and so forth. And let's see, I think I can arrow down. Yeah, arrow down to see the rest of them. So I'm just, but again, for the sake of the notes, I'm going to write all those down, but I didn't have to work that hard, right? I'm lazy. While I'm writing this down for the notes, why don't you punch those into the calculator? We still got to add the dumb things up. And of course, if I had Excel, if I was using Excel to do this, I could get it to add them for me automatically. But add those all up for us, would you, while I'm writing this down, then I'll switch back to the other. So I'm writing 1/4, and inside there I'm writing 1.0625. Again, I'm just trying to give you time to soak on this. I know this is, I know you understand this, but 1.5625, 1 plus 2 plus 2.5625, 3.25, 4.0625. And I got to be careful to like not get too many of them, right? The last one was the one at 2, which is 5. So did all of you say, all right, someone else will do it? I don't know the answer. What is it? What do all those added up to? If I was you, I probably wouldn't have done it because I'd have thought, oh, someone else will do it. Therefore, none of us did it. I'm doing it while I wait for you in case that's the case, but I am waiting.
It's 16. Oh,
go ahead.
It's 16.1875.
Thanks, Eve. So notice what happened here. Like back in the original problem, this was 11.25. The sum of the 4 heights was 11.25, and the width was 1/2. And so by what we did, we now have a sort of much larger heights because now we have 8 of them. It's not like it got way bigger. Do you understand that? But then the 1/4 got smaller. And so if Eve didn't blow it, 16.1875, if I multiply those, I get 4.046. I get a number this time that sort of wants to be rounded off. So again, though, I just want to remind you, this is still too big. I don't know about you, but I'm starting to wonder if the right answer is actually 4. I mean, doesn't it seem like, or does it actually get below 4? Is it actually 3.96 or something? What's your intuition about this? That got a lot smaller though, right? Because the first time we said it was 5.75, but wasn't there lots of waste up there? So of course that was too big. And so this is saying, no, a much better estimate took you twice as long to get it, notice, but a much better estimate is 4.047. Now that's pretty close to 4. So I'm actually guessing it goes below 4 and it's 3 point something. And so that's disappointing. It'd be nice if it actually landed right on 4, but we still have quite a bit of waste up there, right? In our picture, you can even kind of see that. Isn't there still quite a bit of waste up there? 8 rectangles is not enough. But would you agree, for the sake of like an assignment question, or if I put this on the test, I can't really do more than 8 rectangles because the chances of you just not doing something silly here get pretty large. It's pretty hard to get this all right on a test. If you did write out all of these terms like I just did, and then at least I could identify, oh, you got that one wrong, then I can tell you understand the idea, but you just got one wrong, out of stupidity or whatever. Or you got it all written down here right, and you managed to type it in your calculator wrong, and this is wrong. And so But can you also appreciate, in the world that you live in, that computers are really good at stuff like this, aren't they? I mean, we could get a computer to do this for us, write a little routine. I'm sure some of you have done enough computers that you could probably do that. Write a little routine that would allow you to say, how many rectangles do you want? 8, 90, 1,000. And although it would take some time because the computer still has to add 1,000 rectangles together, it's going to do it fast enough that and without mistakes, that might be worth it. And I'd say if calculus was invented now, when we have computers, it probably would have never been discovered that there was a shortcut to all of this, because computers would have done it just fine. You agree with that? I mean, isn't that an interesting thought?
Still seems like there should be a way to simplify that pattern somehow.
Yeah. And essentially that's what drove the, if you will, early mathematicians crazy, and crazy enough that they were able to find that there indeed was. And what I don't want to do actually is spoil this too soon. Like, I'm not just going to tell you today, here's the shortcut, let's get on with it. That's part of the fun of this, is to think, is there some way to kind of speed this process up? Is there a pattern to it? But the thing I wanted you to see here is mostly the fact that you're seeing this get smaller and you're seeing this get larger. And so we're ultimately going to have a battle between 0 times infinity. And oddly, the answer in this case to 0 times infinity appears to be, I don't know, 3.6. I don't know what it is, but somewhere, I mean, there's an area there, right? It's not going to go to 0. There's an area there. I think I want to play with this right now. You do live in an age of technology, and I just think this is something you should know. I don't know if this comes up in your assignment, but I'd like to play with this a little bit in Excel. Could you do this in Excel? Like, could you do what we just did in Excel? I want to see if I can pull this off myself. I've used Excel a lot, so I know the answer to that's going to be yes, but I haven't practiced this ahead. And so let's see. And actually, I encourage you to kind of interrupt here a little bit and you try your own thing. So n is the number of rectangles, and we said 8, all right? Let's have 8 rectangles. And so we ended up with, since our range of numbers was 2, from 0 to 2, that was a fourth. So we know our width is a fourth. So we just need to multiply by a fourth. But how do we get those? How are we going to get those 8 numbers that we added up? What do we do to get those? What do we do to get all those numbers? Let's see, we took, and then in the language of Excel, you have to say equals. We took the number 1/4 and we plugged it into the equation, right? Which involved squaring that number and then adding 1 to it. Isn't that what we did? I guess I don't need that parenthesis there. Yeah, isn't that working? That's how we got 1.0625. And so, gosh, it just feels like I'm just going to have to keep typing this again. This time I'm going to have to type equals 1/2 squared plus 1. Any of you good computer people, how could I do that faster, like than have to type it every time?
You can just drag it down and it should figure out your pattern.
Yeah. Now, I'm not sure about that. If I drag this down, I should never thought about that. Will it eventually figure? It didn't figure it out right away. But one thing I know I could do is go over here and say a fourth and 0.5. It definitely recognizes that pattern. 1 too many. Like, wasn't that the right hand sides that I just plugged in? A fourth, a half, 0.75, so forth. There's 8 of them there. And then how could I make this formula a little simpler now, make it draggable? Instead of saying equals 0.25 squared plus 1, what could I say here?
You can say equal the cell.
Yeah, and where does 0.25 live? It lives in cell B5, doesn't it? So I can say equals B5. And so it's working. And the cool thing is, now that's a formula that basically says equals the cell to the left squared plus 1. So if I drag that formula down now, See how I got all the numbers I got earlier? I'm looking again because I don't remember the 5 all of a sudden. Yeah, last number was 5. That's all the numbers. And then what did I need to do to those numbers?
Add them together.
Yeah, set them up. And there's a formula for that, but in Excel, I can actually just grab all those, and down here in the corner, it says that we got it wrong. That sum is 20.75. It wasn't 16.1875. So did I write one of the numbers down wrong? Did Eve type one of them into her calculator wrong? The rest of you should have been doing this too, and we should have fixed this earlier. Is it just rounding? But I'm going to go back in the notes and cross that out and write 20.75. And if I multiply 20.75 times a fourth, I get 5.1875. So the answer we should have got earlier should have been a little bigger than that. But let's let Excel do all of this. So I'm going to say up here equals sum. And then if I grab all those cells right there, then that tells us the sum. So I'll say the sum of the rectangles, and then the actual area is equal to 0.25 times whatever's in that cell right there. So it didn't work because I didn't put an equal sign in front of it. Equals 0.25 times F2. And so there's our actual area. Now, would you agree that's probably more trouble than it was worth, like the trouble of going to Excel and so forth? But where Excel starts to shine is, what if we bumped it up to 16 rectangles? Could we modify this? Could we modify the work we've done here to get it to give us larger answers? So I'm going to say equals 16. So how do I have to change all this? Let's get
You
even
just
more
have to
fancy.
modify the first column.
Yeah, because now we're going to have 16 rectangles over here. But to get this first number, didn't we go 2 minus 0 divided by 8? So couldn't in this cell, couldn't I say this is actually equal to 2 divided by what's in that cell up there? So it's an 1/8 now. And let's see, what could I do to get the next one? Equals, can I say equals 2 divided by? Equals 2, I have 2 of them, so 2 times 2 divided by that cell up there. Can I copy that down? Is that working? I actually don't know. Is that working? No, didn't like that. Sort of glad that didn't work. In the interest of time, I could just say, well, I in my head, I know that the next one is 0.25. And now because it's just a number, will it recognize the pattern? No, it still didn't like it because that first one was an equation. Let's see. Let's try this. If I say this cell equals 2 equals this cell times 2 divided by, and I copy that down, does that work? Doesn't like that. 6. Oh yeah. The only reason this wasn't working is because when I copied it down, it changed C2 to D. Like I want it to stay D2. So if you put dollar signs around it, that'll stay reading that number 16 right there. That's the thing I was doing wrong the whole time. Anyway, that's not my point here, but do you agree that's working? So my first rectangle is at an 1/8. then it's at a quarter, then it's at 3/8, 4/8, 5/8, 6/8, 7/8, 8/8, which is 1. So there's 16 of them. Does this formula still work? Equals B5 squared plus 1. Does that formula still work? This number here squared plus 1. Yes, that does still work. So here's all my numbers. Does my sum still work? Yeah, no, because it only sums from C5 to C12, and I need it to go to C20 now, so I have to change that to a 20. Does the area still work? No, because I have to multiply by an 1/8. Again, I could automate this a little bit, but do you agree that 16 rectangles, I'm going to have to, this starts to pay off. I mean, if I'm a computer person, if you watch what I just did, because that was a little fast and you think I don't really understand what you said, that went a little quick, fine. This isn't a computer class. But I did get 16 rectangles there without having to add them. And if I automated this, spent a little bit more time with it and automated it a little bit more. But notice, interestingly, the area got below 5. And so would you agree that because this is still a right-hand endpoint, this is still too big? So it got below 5. And so it's rather mysterious what this is. But with 16 rectangles, there's not a lot of waste there. So I'm starting to feel like I'm, well, approaching a limit. I mean, it started at 5.75 and then it went to 5.187. And notice now it's only 4.9. Like it's getting closer to a limit now. Do you see that happening? Let me see if I can even jump this to 32. I don't know. I just want to try this and see if I can make this happen. Does this formula still work? Equals A5 times 2 divided by, I think that formula still works. So I got to get this down to 32. So I think this formula still works. So I think I can just copy it on down. So let's see, these are all of my heights. No, what are these? These are my X's, right? Oops. These are my X values. And then we plugged them into the equation to get our heights, right? So these are our heights. And that formula still works, so there's no reason I can't just copy that down. Notice the height still ends at 5. The right side one's always going to have a height of 5, right? The right side's always going to be 5, so it looks like it's working. And the sum, I just have to update to go down to 36. And the area, I just have to multiply by, well, that was my width right there. So rather than saying times 0.125, now I'm going to say times that cell right there, because that was our first cell. So now it's down to 4.79. You see how it's getting lower and lower and lower, but it's definitely approaching a limit now. Again, that's kind of cool, right? That I just added 32 rectangles, and because I'm getting a little better at it, it only took me, a couple of minutes, less than that, probably 30 seconds to get that done. So can you see how, if your goal was to approximate it, we're already pretty close now, and we just use rectangles. But of course, we're a long way from infinity, right? 32 rectangles is a lot, but we're a long way to infinity, from infinity right now. What do you think? What do you think the limit of this is approaching? Do you think it's going to make it down to 4.6 something, or is it going to stay above 4.7? Maybe it'll go 4.75. Isn't that a nice landing point, like 4 3/4? Maybe something like that. Because I think I have this figured out, let's go one more. Let's go out to 60. Let's go out to 100. I don't know where 100 is, but further than that. So notice it went down to cell 104, and I figured out I didn't have to fix these or these. I don't have to fix those formulas anymore, so I can just copy that down. Notice it's not working because that says 40. Or the right-hand endpoint is not 5 anymore, so something's wrong. What's wrong? I don't remember what I did wrong. Oh, I didn't change this to 100. Is it working? Yeah, that right-hand endpoint is 5 tall, so it does seem to be working. The sum of the rectangles, I have to go down to C104 to add all those rectangles together. And by the way, that's not really the sum of the rectangles, that's really the sum of the heights, because I didn't multiply by the size yet. Notice that went down to 4.7. I just added 100 rectangles. That's pretty legit technology. So it isn't 4.75. I was kind of thinking it was going to be. Is it going to get below 4.7? And where do you think this is going? Would you agree there's not a lot of air in this now? Like, that's pretty darn close. You can't even draw that. Trying to draw 100 rectangles inside that space from 0 to 2. That's going to be tough to do. In the interest of time, let me give you just one more visualization of this that I have prepared. I have a program in Desmos that both visualizes and adds all of these up for us automatically. So let's watch this happen. So I already, just to save time, I already have the equation typed in here. And in my case, what's really cool is I can type in any equation I want. And I said, let's find the area from 0 to 2, which we've already done. And this says 12 rectangles. So n is 12 rectangles. Let's go back to 8 and make sure this thing is working. 8 rectangles. And so there you go. You can see them. You can visualize them. Yeah, I'll just leave it alone. And notice I have left hand and right hand endpoints. I'm going to go with a right hand endpoint. First of all, can you picture that that's what we've been drawing? And that's nice, isn't it? Like, that's a way better picture than the scratchings that I just drew. And it says down there that your approximation of the answer is 5.1875. Is that the answer we got for 8 once we got it fixed? Yes, it is. And then we jump to 16, which all I have to do is fix this, and it gives us another picture. Notice there's still a lot of waste up there. Look at that. I don't know if you thought about that, but see how steep this is up here? There's still a lot of waste up in there. But the answer did go down to 4.9 because there's less waste. And again, I'm going off memory, but I think that's the answer we got when we did 16. And then we went to 32. There's still, because this is so steep, when I zoom in on it, there's still quite a bit of waste up there, but notice the waste is going away, like it's getting better. And as I said before, if we switch to trapezoids, does it make sense 32 would be plenty and we'd have a really good answer? So if we were approximating, we would be using a computer, we'd be using either the midpoint for the height or a trapezoid for the shape, not a rectangle. And we'd be really close and done. What happens if we go to 100? Notice the answer is 4.7068, the same answer we got in Excel a second ago. And notice it starts to look good. It's looking pretty good at 100, but if you zoom in, is it perfect? No, still too big. It's always going to be too big. But let's use this technology to go further then. What if we went out to 1,000? I don't even know if maybe it'll explode at some point here. Notice it seems to be working. And again, doesn't it look awesome? And it says the answer down there is 4.67. So if you will, I'm surprised to discover that, well, it actually got below 4.7. When I zoom in, notice it still looks awesome. But if I get close enough, I guess it is 2. I don't remember how I wrote this because it's been too long now, but notice it's not showing the little green rectangles anymore. See over here how there's a little caution sign. It's basically saying 1,000 isn't working. I can't show it to you. But even without those, do you need that to have the green rectangle to see that there's still some area right there that we're missing? So this still isn't perfect, as good as it looks. And so a second ago, we thought it was awesome, but actually all those are is all the blue heights. So it does appear to be able to give us an answer to this 4.67, but it can't draw the picture anymore. What if I go to 9999? Roughly 10,000 rectangles. Notice it dropped to 4.667. Does anybody have a guess as to what you think it's going to now? What's the limit this appears to be approaching?
Maybe 4.6 repeating.
Yeah, maybe 4.6 repeating. Maybe it's 4 2/3. And for the first time, even though I've taught this class many times before, I actually think that's what it is. I actually think it is 4 2/3. The actual correct, perfect answer with not 10,000 rectangles, but infinitely many rectangles is actually 4 2/3. Let's add another 9 and see if it can handle that. Notice it says it can't. Do you see how it's like right hand approximate? It's like it can't do it now. It's like it's too small and it won't do it. That's interesting. Didn't know that either. So you can appreciate that, if you will, the ancients did not have access to this. They did not have the ability to add 9,999 rectangles. They didn't even have a calculator. So even if they were patient and wrote it all out, they just can't get an answer like this by cheating, which is effectively what we're doing. But can you see that if there is a way to do this without actually having to do it and not using technology, then the fact that we could actually get an exact answer to this, and that it appears to be 4 2/3, or at least we're wondering if that's not the limit this is approaching. And as I said, it's interesting that we had to go so high to even have a guess. I wasn't sure if it was going to make it below 4.7, but it did, apparently.
Why is one of the like parts of the function called magic? Like, are we?
Yeah, this is magic in the sense that these are commands, if you will, in Desmos that are pretty deep. Like, people have found a way to trick Desmos into doing this for us, if you will. And all I tried to do with this, because I found this online, like somebody had made it, and I attempted to figure it out, and I didn't even fully understand it. And so I messed around with it some, but I sort of left. I wanted to be able to see everything that was going on here. And ultimately, that was the stuff I wasn't totally able to make sense of. But even here, can you see that? Remember the heights of our rectangles? There was a height, and then the height plus 1 width, and then the height plus 2 of those widths. Isn't that how we got those X values? Like we had an 1/8, and we had 2/8, and we had 3/8, and we had 4/8. That was our X's that we plugged in to get our heights. That's a list of all of those.
Does this work with other equations other than x² + 1?
Yeah. So let's play with one real quick, since we don't have enough time to start something new anyway. Let's look at 1 divided by x, and let's get it back to, like 12 rectangles or something like that. First of all, do you agree that that's still a right hand endpoint based on the pictures that you see? Because I lit up the right hand endpoint version. Well, do you see how this first rectangle down here, defined by this space right here, and notice 12 is a pretty weird number to pick, because dividing by 12 is kind of a mess. It's a little bit messy because I can't tell where I am right there. Do you see how it doesn't land on a box? 12 is kind of a weird number to choose for rectangles. But how tall is that rectangle? We'll see how it's defined by not its left side, but by its right side, where the right side hits. But can you tell from this picture that the answer that we're getting here of 3.103, and by the way, let's change something else. Let's go from 1 to 4. So do you see I'm saying I'd like to know the area of this from 1 to 4? Does it make sense from the picture that this is an underestimate? The area they're giving us here is 1.297 based on the picture. Do you agree that this right-hand endpoint is an underestimate of the correct answer to the area under the curve? And if I increase the number of rectangles from 12 to 120, this 1.29 just got bigger, right? Because now the wasted areas just got smaller. So it's still an underestimate. So you can't just say a right-hand endpoint's always too big and a left-hand endpoint's always too small. It depends on the curve. This curve is decreasing. So a right hand is actually giving us an answer that's too small. And so this is working its way up to the right answer. Again, I find myself curious. I wonder where this is headed. If I take it out to 999, I don't see that 1.385 as a recognizable decimal. I don't find myself thinking, oh, I see where this is going. I wonder if it makes it to 1.4, like that's a recognizable location. It seemed to handle it if I threw one more 9 in there. So let's throw one more 9 in there. Notice how it said it can't draw the picture anymore. It is giving me an answer of 3.86, 1.386, but I can't tell like where that's going. I can't, is that landing someplace? Like I can't cheat and guess the perfect answer. And by the way, I'm still not sure the previous problem was actually 4 2/3. I'm just kind of guessing. It looked like it was. But that's it. It's 9:20. I got to let you guys go. That's Calc 2 right there. We're finding the area under curve. And embarrassingly, again, we don't tell people this. We're just filling up these curves with a bunch of rectangles. That's it. That's this whole class. And oddly, it turns out to be calculus that's going to let us do this without having to do it. And it's weird that it turns out that last term's topic relates to this term's topic. It turns out that slope and area are actually related. And Jesse was working pretty hard to try to figure out, like, can't slope tell us something about, where this is going and so forth. And you're on to something, Jesse. The fact that these two topics are actually related to each other, and it's calculus that it's going to let us, and it's the calculus that you already know that's going to let us find these areas without having to add up thousands of rectangles. And therefore we can just leave them rectangles. We don't have to use trapezoids and so forth. So we're going to pick it up there tomorrow. I'd encourage you to get into My Open Math and begin wading into the assignment. You have the basic concept in the notes that I shared here about just adding up some rectangles. And that's all you need to do for 5.1 is just add up rectangles. And I can't remember, tomorrow we have another day to talk about this. I can't remember if the assignment asks you to try to add up trapezoids or to use the midpoint for the height of your rectangle, or sometimes use the left side and sometimes use the right side. That's really just what we need to practice tomorrow. But I don't have anything else conceptually that you need to understand right now to get 5.1 figured out. So wade into it.
Mind if I stay a bit?
Yeah, so boogie off if you're done. If you want to stay after and ask questions about conceptual things, or if you're having any trouble kind of getting going in the class or anything of that nature, feel free to stay after, but feel free to bug out because I'm not going to say anything other than just have a discussion for 10 minutes with whoever's left.
Yeah, I'm trying to enroll in the class of My Open Math, and it's telling me that I'm already enrolled. Yeah, I don't see it.
Let me
check under your hidden courses. Sometimes it can get thrown into the wrong.
I did that.
Let me see if I can find you. And did you try to enroll, Justin, after I sent you that code? Hit the space bar, I can't hear you.
Oh, I just tried to enroll this morning with what was on the syllabus.
Well, you weren't able to enroll because the class size limit is 30, but I sent you and Caesar the code. But again, our computer system has been wonky, so.
I'm registered. Yeah, I'm registered in the class I'm talking about on My Open Math. It's not letting me enroll.
I see. Okay.
into the class for some reason. Like it keeps telling me that I'm already enrolled in.
Yeah, let me see if you're in there. 4 people have enrolled since we started class today.
I think it just gave me the same thing. I just tried to enroll and it said that I was already in there, but I'm not seeing it.
I literally just did it and it worked for me. There was like the codes and stuff in the email.
Yeah, I sent what you need on the syllabus to get enrolled as far as a code, a class code, and so forth. Yeah, I don't see you in there, Justin. I don't understand. Who else said they tried and didn't get in there?
That was me.
Cheyenne. Says you are enrolled. So Felix, you said it let you in. Oh yeah, I do see you in there now. So Felix got in and I see you. You're already in it. It's not something I've encountered before. And you guys did it last term, so it's not like you haven't done it before. So. Huh. You guys weren't, for some reason, trying to enroll in 251 again, were you?
No, I'm not. It's the current code in the current. I thought that too, and I was like, that's why I went back and looked at courses, and it's only 251 is in there. I don't see 252, but I've tried it multiple times. Every time it just tells me that I'm already enrolled.
I'm scratching my head, not thinking. Well, I guess let's give it a day and see if it's something with the system itself. If either of you, Cheyenne or Justin, figure out something that you did wrong, please send me an email about it.
Hey, Doug.
Yeah.
I had the wrong course ID number in my syllabi.
I tried signing up and it says it's the incorrect key.
You guys got to make sure that for the enrollment key, there's spaces between winter 2021 and then Gardner.
Yeah,
and the capitals matter too.
Yeah.
Are you guys copying from like the actual syllabus or like the My Open Math page? Because there were like 2 separate places where it was.
I did the syllabus from the email.
So
yeah, I used the login instructions part and that worked for me.
So Justin, what's your not enrollment key? What's the course ID you're using?
I just pulled it up straight on My Open Math and shared it with you guys. It's not impossible. I copied it wrong in the syllabus or something. But I thought all you guys needed was.
Yeah, that's not the ID I have in the syllabus. That must be the problem. Because.
Well, how the heck did the rest of you get in there then? Where did you? Maybe
I don't.
Whatever. Type that in now and let's see if it works.
It worked.
Huh.
Now. Yeah, or there it is.
Capitals or my syllabus is screwed up. I have no idea how I could have possibly
The syllabus says no number.
You emailed us like the syllabus might say the wrong one. Then there's like another attachment on the email that says my open math login. There's like there's 3 attachments with it, I think, with the email.
Yeah, I sent you a My Open Math one. So you're saying the syllabus and the My Open Math one don't agree?
Yeah, I got mine from Blackboard. I didn't get that email because I don't think I was actually registered in the class in time to get the email about with the syllabus. So it might just be that the syllabus on Blackboard has the wrong number in it.
Yeah, that could be one of the things. I think I remember updating this syllabus. I think I updated this.
Okay, yeah.
I changed this to winter 21, and I might not have. Maybe I screwed that up. And so I think it's my
Yeah,
fault.
this one worked. The number was different than the one that's on Blackboard.
Blackboard. So I changed it, but didn't change it on Blackboard. So it's totally my fault. I apologize.
There's no worries. I just felt like I know I'm not doing.
Well, good. I'm glad that's sorted out. I'll make a list of who's in the class for tomorrow and just kind of make sure everybody's on board. But I'm glad you guys stayed. Cheyenne, are you in now too then?
Yeah, I just got in. It was the syllabus from Blackboard. It has the wrong number in it.
Oh.
Hey Doug, just triple checking. I got in just while we were talking to make sure mine worked too. But do we have like attendance quiz or something we need to take, or are we just like signed into Blackboard that we're in the class?
You don't need to do any of that. I'm looking at the list. Like I can take attendance after class just because of who showed up to Zoom. So
Awesome. Thank you. See you tomorrow.
we're good. See you tomorrow.
Thank you. See you tomorrow.
All right. See y'all.
So I had a bit of a question. Hopefully it's not a very big one. I was just getting a little bit curious when I saw that thing you pulled up in Desmos, and I was wondering if any of these kind of turn into some more interesting numbers, like if we get like pi and e and that kind of stuff showing up in these areas.
Yeah, you do. You get all kinds of crazy answers to this. So they're not always nice. They're again, I'm starting with the simplest curved equation I can start with when I pick a parabola. Does that make sense? As an equation, it's the simplest one I could pick. But if I start picking like the sine of x, e shows up in that world sometimes, but pi certainly does. Pi shows up in that world, so you can end up with an area that's got pi in it, for instance, in that world. If I throw an exponential equation in there, that's kind of where e shows up a little more naturally. So you could end up with an area that's, you might get lucky and it is e. 2.718 for an area you might recognize. Hey, isn't that e? But what if it was like e squared or e minus 2 or something like that, or e minus 3/4? You wouldn't recognize that as a decimal. And so yeah, I mean, these actually turns out all have exact kinds of answers, and it's calculus that's ultimately going to give those exact answers to us. And yeah, you're going to get answers that are kind of all over the place. And because the trig equations, and as I said, I already hinted that it's related to what last term. Like last term, if we said, hey, look at that tangent graph, I wonder what the slope is over there. Well, we found out the derivation, the derivative, the extract from the tangent equation is secant squared. The derivative of tangent is secant squared. And so if you plug your location into secant squared, that'll actually give you the slope on the tangent line. And the same thing's going to happen this term. It'll be something like, hey, I wonder what the area is under that tangent curve. And you'll find out that the integral of tangent is logarithm or secant cubed or something like that. And if you plug the numbers into secant cubed, then it'll actually give you the area under the tangent. And so that's kind of the connection ultimately from last term. So it's actually kind of weird. So yeah, you'll get all kinds of crazy areas, but they'll definitely be unrecognizable decimals left to themselves as they are right now.
Yeah, I just think it's always fascinating whenever those kinds of numbers are like showing up everywhere, basically.
Yeah, you're absolutely right. It's crazy how how many places E and pi sort of show up in worlds that you wouldn't think they should exist, if you will. And yeah, it's particularly interesting when it isn't just and again, that's one of the things that kind of drove the ancient mathematicians crazy, is they had no trouble if the answer came out even something crazy like 279 over 19. I mean, that is going to be a crazy decimal, but that decimal is coming from whole number divided by whole number, which mathematicians call a rational number. They'd say that's rational. And so as weird as the decimal version of that looks, 279 over 19 is a nice clean answer to them. And so they have no problem with that. But what if the answer is E? Well, E isn't ratioable. It is not possible to write that particular decimal answer as a fraction. And on a simpler level, it's not possible to even write a patterned fraction, a patterned decimal like 0.12, 112, 1112, 11112. Like there's a pattern to what I just said, but you can't write that as a fraction. There is no way to ratio that. It's non-ratioable. It's non-rational. It's irrational, mathematicians say. And so the fact that there's answers to real questions that have these crazy decimals, and some of them are, if you will, popular enough or show up often enough, which is what you're getting at, Felix, that somebody said, hey, let's give that one a special name. Let's call it E. Shows up so much. And we'll name it after a guy named Euler, whose name starts with an E. So we'll name, and pi is the same way. Those are the two kind of classic famous ones. But there's other ones. There's one called phi, 1.518. There's another one that you've never heard of before that shows up in nature that also has a name. And so sort of the famous ones, the ones that keep showing up, if you will, that is a tremendous fascination. You're absolutely right, Felix. Excellent point. Amazing stuff.
Can you hear me? I have a question.
It's kind of quiet.
Not sure how to fix
Something,
that.
Becky? I didn't hear you. Get closer to your mic, up your volume or something. I don't know what's wrong there, but.
1 second. Let me try and fix it.
Well, I have a question about my work schedule.
Yeah.
So basically what my work schedule is going to be is like a Thursday, Friday, Saturday
Mm-hmm.
thing. And I was wondering if